We are JHM, and this is the production presentation for Worcester Wasteland. At the start of planning, we wanted to create a new engine from scratch based on designs and ideas from the two engines last year. However, we quickly realized that within our time constraints this was not feasible, so we ended up working on and improving on one of the engines. The initial design was to make every manager a child of engine, which was a singleton pattern, and all managers were accessed through an interface. The engine we ended up with using did not follow this design, with each manager being a separate class altogether, though the managers are indeed singleton, with some of them being purely static instead. The managers themselves are accessed directly, but all entities within the managers are accessed via interfaces. The original plan was to have an engine abstraction layer to link Game 1 to the managers. However, the current engine allows Game 1 to access the managers directly and performs any necessary setup. The idea being that everything in Game 1 will be replaced in the future with a visual editor, allowing a developer to create entities and scenes, etc. With this not yet implemented, Game 1 is a temporary solution, and a lot of it is currently hard-coded. The entity creation pipeline hasn't changed all that much. However, the original design had the scene request entity creation, whereas entity creation is requested in Game 1 and then added to the scene. Entity is an empty extraction class, with BG entity adding some more engine-specific data members and methods. The children of BG entity are what get initialized in the game, such as the player character, menu items, etc. Entity brain contains the AI, with player control inheriting from this and replacing the AI with player input. This was the initial design for AI, where it would follow a path until it sees the player, in which case it would pursue the player until it either loses or catches them. The current version of the AI follows the waypoint path derived from Dijkstra's algorithm and can chase the player. However, we have not yet implemented any form of sight in the AI, so they do not naturally switch to the pursue state. Instead, for the sake of showcasing the behavior, they simply do it on button press. This is something we intend to improve upon for post-production. Collision in our engine is made more efficient through quad trees as our spatial partitioning method of choice. It starts by creating a singular quad tree node which detects all objects inside of it. If objects exist in different quarters of the node, it will split into 4 subnodes. If it cannot split, it checks for collisions. All subnodes do the same. This ensures that objects are only being compared to objects in the same subnode for collision, saving a lot of processing power. A quad tree manager creates the initial node on scene change, which may then split into subnodes, which may split even further. We chose Dijkstra's algorithm for our pathfinding. The key thing to note about this is that paths to waypoints are weighted, so a straight line is not necessarily the best route. Currently, waypoint paths are weighted manually. The example shown here demonstrates how a straight line to the destination would take the plane through a storm, which is weighted higher than going around, so the plane chooses the physically longer but lighter path. The steering is performed by a steering motor, which is fed the location of the entity and target it needs to get to. These vectors are subtracted from each other, normalized, and multiplied by a max speed to get the resulting direction. This is done on every update, which, when combined with length checks, steers the entity to where it needs to go. This results in more natural curved movement as opposed to instant direction changes. And now we will show you a video of the prototype in question.